Hello, everyone. Welcome to SQL Plus for Big Data, Same Language, More Power. Thank you for being with me today. Let me share my screen first. Cool. So, when we talk, I work as developer advocate at Couchbase, and although I'm developer, I have been talking about databases for a few years now in conferences. And one of the things that kind of blew my mind when I first started talking about this topic was that whenever I mention some core languages, one of the most common feedbacks that I hear was that, hey, querying data is a problem that we already solved. Why you guys are using a different query? Why you just don't use SQL? And what I realized was that there is a lot of lack of understanding of how things work under the hood. And then I decided to create this talk, which is essentially just a theory behind NoSQL and relational databases, trying to explain, hey, why there is need for a core language, a new core language, and why we need to create a standard as well on the NoSQL world to unify how we query NoSQL databases. Cool. But before I explain that, I need to talk a little bit about how we got where we are today. If we zoom in on the architecture of a processor, a modern processor, by the way, this is kind of old, but most of them use the same architecture. For me, it was kind of mind-blowing to realize that roughly 85% of the CPU here is just memory, and 1% is actually dedicated to compute. So if you buy a processor for 100 euros or dollars, like just €1 is actually compute. Everything else is just a fast memory. And even when you go to more modern architectures, this is of course a little bit old as well. This is already this is a quad core, but you see that's pretty much the same pattern. We see the same pattern here. Pretty much the huge majority of the processor is dedicated to memory. And the reason why we have such architecture is because of an issue called latency. And as you see, the far we are from the compute, the latency increases dramatically. So to access data on L1, it usually takes around 1 to 3 CPU cycles. But to access a remote DRAM, you see that okay, the time has increased more than 100 times. And the problem with latency in general is that this is an issue that is very tough to solve. If you think about it, in the last 20 years or so, we have increased the disk. We have increased the network, but latency is pretty much the same, right? Because in order to decrease latency, we have to come up with new material, invest like millions of dollars just to have a marginal improvement on latency in general. And what we decided to do is to, instead of improving latency, we decided to increase the bandwidth. So we started to parallelize stuff, right? So instead of just having, for instance, a single CPU, which is more powerful. We decided to have multiple CPUs inside one single unity. And same with networking, same with disks, same with other stuff as well. We started to parallelize things to make them look faster. Okay, why this is relevant to us? Because this is essentially the same problem that we have with relational databases. They, even though they have been out there for 20 years or so, I mean, some of them more than 20 years, they still, the model still breaks when you need to run it distributed because of latency issues. Let me just give an example of that. For instance, here, let's say we have two tables. One is the user and other the user roles. And naturally, you have as well a roles table here. And in a relational world, those two tables, they live in the same node, and you can join those two tables as you wish. And joining your tables is actually a very fast operation as long as your tables are properly indexed. So if you have like 1 million rows joining two tables, the operation of joining two tables will cost you just a few microseconds, considering that, yeah, obviously your tables are properly indexed. And here life is happy because everything works great. However, when we want to scale relational, things get a little bit complicated. For instance, the way we scale relational database today is essentially by duplicating the whole database. So quite often we see an architecture where, yes, you have the first node where you can read and write, and then you have a secondary node, and which is a kind of a replica of the first. And then you set up some kind of a replication channel between those two nodes. The replication could be synchronous, so which means that when you commit data to the first node, you also have to commit data to the second node as well. Or it could be asynchronous, which means that you might have some dirt reads because your commits, you might read something from the server 2 that has already been changed on the server 1. And the natural this is essentially how I would say 9% of the relational databases work. And the natural question that I hear is, hey, why relational databases are not running distributed already? And do I need those NoSQL databases at all? Because can I just expect that, I don't know, maybe 2-3 years from now, Postgres, MySQL will all run distributed? And in reality, the problem is much bigger than that. So if you make a relational database run distributed, you might have something, your data might end up distributed between multiple servers. So let's say I have my user, and my user data, the user table is in one node, the data, and then the user roles are in another table, and then maybe preferences is in another, naturally another table in another node. And when I need to load back this user, to memory, I have to go through all those nodes just to get the data. And the problem is I potentially don't know those things in advance, because when I load the user, I get some IDs, some foreign keys there, and then I have to find where those foreign keys are in the database, and then load the rest of the data, and then maybe they might have some other foreign keys there, and I need to traverse this data in order to load the whole thing back. And that's essentially why some of the problems that we have relationals when they run distributed. That's why even though they have been there for a while, I would say the huge majority prefers to stick to a single node. This is naturally something. This behavior was by design, so most of you might have known that EFCOD created the relational model, and it was originally designed to run in a single machine. That's why, yeah, when you try to run it in a distributed environment, it kind of breaks, because the original design to everything in mind was designed for a single node. But the interesting thing here is that the SQL wasn't created with relational. It actually came up a few years later with with Don Chamberlain and Raymond Boyce. They created this SQL language because back then, when the relational model was created, they used a proto language called Alpha, which was using essentially mathematical approaches to core data. And then Don Chamberlain decided to say, "Hey, why not use a language that is English friendly to query data?" One interesting thing on this is that when SQL was proposed, it was criticized a lot, because back then the way you would get data is to directly access the disk and find the data you need. And the common mindset back then was that going to SQL to get the data was a waste of resources. So for a few years, no one cared about SQL until Larry Ellison from Oracle decided to use SQL as the query language for Oracle, and then this was when the whole thing exploded. And I don't know, 50 years from now, from that day, well, SQL is almost a synonymous for relational. Yeah, and I actually had a chance to work once with Don Chamberlain. I had a chance to review one of his papers, and I actually got a comment that got accepted. So this is my most one of my achievements so far. But I guess the world changed, right, since SQL was created. So the way we deal with data and applications in general 50 years ago is completely different than the way we deal with data today. So the applications today are far more complex than what we were creating 40 years ago. So there is in the last, at least in the last 15 years, growing criticism around relational and SQL. And I guess one of the most important of them is, and most developers kind of fail to realize, is something called impedance mismatch. So on impedance mismatch, there is something called, essentially it means that the way you deal with data in your application is different to the way you deal with data in the database. So for instance, if you have a shopping cart, and inside your shopping cart you have your shopping cart items, reason why a shopping cart item should exist outside of a shopping cart. It only makes sense to exist inside a shopping cart, right? So quite often we treat in your application, you treat your shopping cart as kind of a unity of data, pretty much like a user as well. You have your user, you have preferences, you have rows, address, and other stuff. But in your application, you treat your user as a whole. But when you need to store this data in the relational database, you have to split it in tables. And the reason why we do this kind of thing It's just because the relational model forced us to do that. In theory, a database should store the data the same way that you do with the data in your code. But the relational model, because it was designed like 50 years ago, it forced you to store everything in tables, in boxes, and you end up forcing to split your unity of data into multiple tables. And if you're old enough, you probably remember that back then we used to have these huge DAO classes that essentially just insert data on the get your object and then translate it to relational. And then when you need to query data, we would query the relational database and then translate it and get all the columns and translate that to an object. It was rather painful to do this manually. I guess today very few applications actually deal with SQL directly. Most of them are using something called object relational mappings. So like in Java world, we have Hibernate and JPA in general. On the .NET world, we have something like Link. But if you think about it, RMs are just a workaround, right? The reason why we have object relational mapping frameworks is just because we have an issue between our application and the way we deal with data versus how relational databases deal with data, because they haven't evolved a lot in the last 20 years when it comes naturally to the data model. Well, everything that I said here is not something new. Essentially, the problems with scalability and querying are things that both Google and Amazon had issues already around the early 2000. And then I think both of them were using Oracle, and they were hitting some limits there. And they started to looking for something else, like, okay, what else can we do to be able to grow as much as we need. And then they decided to create a database, create new databases themselves, and they come up with two different approaches. And around 2005 and 2006, they published two big papers, two famous papers. One is called Dynamo, the Dynamo paper, which is not the table that originally the DynamoDB and Dynamo paper are different things. So it doesn't describe the paper is not describing DynamoDB. So it's just the first name that they gave to this database. And then we also have the big table paper from Google. And those two papers, they were very influential in the Nosql world. And potentially they were, after this, we had the big bang of NoSQL databases. So a lot of folks started to implementing concepts explained on those two papers. And roughly, if you consider that everything that is not relational is a NoSQL database, that's why I kind of hate this term NoSQL. But still, it's what most people use. So if we consider that everything else that is not relational is a NoSQL database, then we have roughly more than 200 NoSQL database today. And most of this was thanks to those two papers. Another interesting thing about the Dynamo paper is that they decided to do something called denormalization. So instead of using tables, they decided to introduce some sort of hierarchy in the data model. This, for instance, this is not, they didn't use JSON, but this is just for you guys to understand uh, the this kind of hierarchical structure. It could be XML, it could be YAML, whatever. The important thing here is just to be able to nest data inside another data. And when they did this kind of thing, what they realized was that around 70% of the operations were just using the key. So in this case here, to get the whole user, I don't need to make any joins. I can just, let's say, if the ID of the document is the username, I can just go to the database and ask for the user, and I will be able to load the whole thing back with no joins. And this essentially makes it possible to create a distributed database, because now we are avoiding those cross-node joins that we have in the relation database, right? So loading a user is not problematic anymore, because I can everything is in a single unity, and when I load this unity, doesn't matter where the cluster is. I'm not making any cross-node joins. And only essentially 10% of the queries that they were making was actually involving multiple document types. And because of this, you can actually avoid those cross-node joins by creating indexes, because it's just 10% of your queries are doing those sorts of operations. So long story short, you could have in a distributed database a performance which is as good as relational for non-ad hoc scenarios. Another interesting thing of using a different data structure is that it is also less transactional. So, for instance, in a relational database, if you need to insert a user, you probably you need to start the transaction, insert the user, insert the roles, insert preferences, and then finally, when you finish inserting everything, then you commit the transaction. And naturally, if something goes wrong, then we have to roll back the whole thing. While in a document database, because it is a hierarchical structure, it is already all or nothing. So, or you insert the whole user, or the whole operation fails. So you don't need any sort of transactions for that. I think my camera just okay. The camera is back. So you don't need any kind of transaction control for single document operations, and you can also make multiple document transactions in Nosql database today. I guess this was one of the biggest improvements on Nosql world last year. Most of the vendors essentially release support for transactions between multiple documents. But the rule of thumb here is that you don't need a lot of transactions. You don't need as many transactions as you need in relational when we are dealing with a Nosql database, because of the data structure is already atomic. Cool. Then I guess we finally reach the main point of the presentation, which is, okay, that's good. Feels like NoSQL, this hierarchical structure, is the way to go to store data instead of using relational. But how do we query this data now, right? Because this is not flat data anymore. We can't use SQL. So how can we query this kind of hierarchical structure? In the past, I guess a lot of databases decided to create their own query languages. And don't get me wrong, some of them are really good. Some of them are, I guess, even for some famous NoSQL databases, I guess they invested too much on their core language, and now it's too late for them to go back and say, no, 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 we uh, this approach that we took is not good. But in general, what we noticed was that, okay, although there is some amazing languages out there, people like SQL. So even in the academy and developers, we all, that's what we learned in the college. So we like SQL in general. We don't want to learn something else. And another issue with NoSQL databases is that, sorry, because they own, they each one of them created their own language, it's very hard to migrate from one NoSQL to another. Essentially, because the core language is different, and then it requires you to um, rewrite your whole persistent layer just to migrate from one NoSQL to another. So ideally, we should come up with a standard for NoSQL databases as well, pretty much like we have with relational. So thinking about this issue, some researchers from the UCI decided to tackle, hey, is there a way of using SQL and change SQL just enough um, to make it work with hierarchical data? And a few years later, they come up with a solution called SQL Plus, which is a language SQL compatible, so it is SQL. You can, and in some cases, get the same query on. I mean, as long as you have the same structure in NoSQL database as well, you can get this, run it on a NoSQL database, and it will work with SQL++. And they published this paper in 2015. And a few years later, a lot of other universities started to research around this language as well. And then in 2016 and 17, some databases decide to implement this specification. So we have Couchbase, the company that worked for AsterixDB, Apache, AWS PartQL, which is still our early product of AWS. But they are all using SQL++ as their standard language, and that's really one thing that we are pushing here to also adopt this standard and make it easier for you to migrate between relational databases and then create a standard on this area as well. Even the father of SQL, Don Chamberlain, also he was retired, and he decided to come back and start researching and talking a bit about SQL++. He is a big supporter of this core language, and he wrote a book called SQL++ for SQL users that you can download for free. But the question here is, okay, I have been talking about all this stuff. The big question is, okay, why SQL+ special? Why is it different than other core languages? Essentially, SQL++ is backwards compatible. So you have joins, you have group bys, you have order bys, you have union limits. So pretty much everything that you're used to in SQL 8.9, which is what most of us are used to, you can do with SQL++, the same syntax. For instance, here is an example in SQL. So let's say I have here a table with the 3 columns, so foo, bar, and bass, and I can select foo bar from my table, so just name a table where bass is equals to QUX, right? So this is just a standard SQL example. And if you notice, the query is the same in SQL++. So here we have 3 JSON documents, and then we can make the same query in SQL++, but the structure, the underlying data model is different. And in fact, what people usually say, and even done sharply, is that, okay, if you squint just enough, you kind of see some sort of table pattern here between JSON documents. Going further, this is just some other examples of how SQL++ works. So you can see that, yeah, the select is pretty much the same as you would do in a relational world. Same with the count, and you have group bys and having everything else. Deletes is pretty much the same thing as well. The only difference, naturally, is when you are inserting data, because now, okay, yeah, we are inserting JSON document. So the syntax is you insert the ID and then the whole body of the JSON document here. So this is, I guess, the only major difference between relational and SQL, the SQL++ and SQL. The SQL++ has some extra powers because now we are dealing with hierarchical data. One of them is the capability of saying that something is missing, and missing is different than new. So I can write something like select star from my bucket where a bass is missing. So you see here that in the first document, I don't have bass here, the attribute called bass. And in the second document, bass is new. So my query will return just the first document here because the attribute bass is missing. If I want to query where bass is new, I need to say where bass is no, and then I will return the second document. Or I could say where bass is not missing, and then I will return the third document. This is some of the extra things that you have to deal with, because I would say pretty much all JSON databases, they have JSON or document database in general. It doesn't have to be JSON, but they all have flexible schema. So you always need to be aware that there is this difference between a missing and a new value. Another power of SQL++ is how you access nested entities. So let's say you have here, you want to select the city of the users. So you can simply traverse the whole structure using the dot operator. So if you want to select the city, you can simply select the select address.city from my users. This is naturally nothing new. Probably you guys have been doing this with your ORM frameworks, but remember, this is something natively supported by my camera, because I see that this is going on and off all the time. Cool. So you can navigate through the structure here using the dot operator. And another interesting thing as well is that there are some extra syntax to deal with arrays. So let's say you want to select the first favorite food from a user. you can simply refer to the attribute name and then the index of the value. So in this case here, if I want to select the favorite food from the users, I can just write select favorite foods and then 0, which is the first index from my users, and I will get the first item of this array. Or let's say I want to select all users which have pizza as their favorite food. So instead of using the index, because I don't know where in the favorite food where pizza is in their list of favorite foods, I could use a different syntax here, and then we have something called an operator called any, in, and satisfies. So essentially, in this query, I say, hey, select all my users where any f, so f is just an alias for each item on the favorite foods, in favorite foods, so I'm referring to the attribute that I will iterate, satisfies f equals to pizza. So the beauty of this thing here is that we are querying an array with a syntax that, potentially if I show you guys this thing here, you guys would not even know that this is not a SQL. It looks like SQL, even though we are dealing with a hierarchical structure. We also have another important superpower as well, which is called a nest. This is a little bit more complicated. So with a nest, I can essentially navigate to the structure and get just the data that I need. So let's say I don't care about, I have a parent or a user, and then I have here the children of this person. And I don't care about the person, I only care about the children's. So if I want to query some nested entity, I can use the word a nest to say, okay, ignore everything that is up above. I only care about this section of the document, and I want to query, it. So here in my case, for instance, I say, hey, I want to select everything from my users, which is my bucket, and I want to navigate to the structure and unnest children. So from now on, I'm querying just children. And I want to select all children where age is higher than 10. So this is pretty much how a nest works. And yeah, I guess congratulations, you just got a crash course on SQL++. This is, I would say, 80% of everything that you need to know with SQL++. Everything else that you know in SQL will pretty much work in SQL++ as well. One common question that I see is, hey, what about SQL 2016? So SQL 2016 introduced some support to JSON, and essentially Don Chamberlain also did a comparison on that. He published a white paper comparing SQL++ with SQL 2016. And the conclusion was that, hey, we are dealing with different things here, right? So SQL 2016, which is, I guess, the latest spec of SQL, introduced some support for SQL, for JSON, but it's not designed to, it's just for like small use cases. If you need to query your JSON a lot, is rather difficult. Like the query on average will be 3 to 5 times bigger than SQL++. So quite rapidly, you query your JSON data a lot, you're gonna have a bad time. Another common thing that I hear as well is, what about Postgres? So Postgres introduced support for JSONB. And yeah, I guess it's pretty much, it falls in the same bucket as SQL 2016. There is some support for JSON. It is good if, okay, you need to store some data as JSON, and it is definitely not something designed to be used as a NoSQL database. I think some developers or some articles in the web say that, yeah, you don't need NoSQL databases because they already have JSON in Postgres. And whenever I hear this, I automatically understand that they have no understanding of how things actually works under the hood, or they never use this in a real scenario. But for very simple use cases, yeah, JSON Postgres on JSON-B on Postgres could be helpful for you, especially if you just need to, let's say, store some requests and need to query those JSON documents at all. And the problem itself on Postgres is that querying those JSON columns are, I would say, a little bit complicated. So here you see the syntax in Postgres and the syntax in SQL++. And surprisingly, the syntax in SQL++ looks more like SQL than the syntax in Postgres itself. So even though I wrote this presentation and I wrote those queries, still whenever I come back to this, it's kind of I need to wrap my head around this to understand what's going on the query on Postgres. Yeah, and this is yet another example. You see that if you need to update the query, it gets even more complicated. So this is a query in SQL++, and here is a query in Postgres. And some other people also talk about, hey, why not Java has a higher language, a query language. Other databases, other languages also have the same type of higher level language used for ORMs. Why we don't simply use them? And there's some other issues with it. One of the issues with this kind of language is that you can simply navigate through the joins, and this is something for distributed databases. It's not recommended that joins would be that transparent, essentially because of cross-node joins, you might need some indexes and some other stuff. So doing this kind of stuff will probably simulate some bad practices. And as well, on Java persistent core language, for instance, you can always select directly the item that you need, and when you have this kind of hierarchical structure, you need to navigate through the structure, right? So you cannot access the ordered item directly. You need to go to the order and navigate to the ordered item, and that's yet another issue with this kind of approach as well. Cool. Yeah, I only have a few minutes left, so I would like to give you guys just a single demo. This is the Stack Overflow survey. Everything that I talked to you guys is actually production ready. So we have been using this thing for at least a few years, almost 5 years. And this SQL++ is a standard way how we query Couchbase. And yeah, here I have the Stack Overflow survey, and you can just write simple queries. So here, select star from stack, where the containers is one of the questions, where I do not use containers, and I can use a limit 10 here. And you see the result is actually each result is a JSON. So because this is, in this case, that we don't have a lot of hierarchical structure, you can even visualize this as a table, and you can also see the plan, so how the query is executed. So this is essentially some values to understand where you spend most of your where the query spend most of the time. And yeah, just 1 minute left. So let me just go to this, and you can essentially write very complex queries. So, for instance, uh, where is the average salary of someone working with Couchbase, for instance? And you can write some queries like, oh yeah, here I'm using temp tables, I have group bys, I have order bys, and you can execute the whole thing here and see the results and say, okay, yeah, in Russia, uh, let's say let make other here. So in no wait, wrong query. So here is the salary. So when I execute this whole thing, you see that okay, here I have temp tables, I have average, I have group by, everything that you have in SQL you have here. And you can see, oh yeah, so on average salary, someone working with a Couchbase in US will earn something around this and that. In Europe, that's the values and so on. So very, very similar to SQL, but you're querying a hierarchical structure. So I'm kind of, just 1 minute over my presentation. So I'll stop here and answer questions. So thank you very much, guys, for attending this session. So let me just go back to the presentation, to the questions. So regarding SQL++ being implemented by MongoDB and Elastic, this is definitely something that we are trying to push because the most important thing for me is being able, because it's already been adopted by a few NoSQL databases. So you can write, let's say, if you are using Couchbase and you decide to migrate to another to AstroXDB or what else, or other NoSQL databases that are implementing this. It's very simple. It'll be almost as simple as migrating from one relation to another. So pretty much an easy migration. But the issue is that in the database world, everything happens slowly. And I guess MongoDB, they have this aggregate framework that to be honest, I personally am not a big fan of, and they have invested a lot of time on it. And this is one thing that we are trying to push, like this is not something that we define, so it's an open standard, and trying to convince other databases to implement this as well. And that's exactly why I'm speaking here today, because we need to make this standard popular. Regarding impedance mismatch and nested entities, your thoughts about repetitive data. There's a way to reuse the data in SQL++. Should I worry about it at all? Yeah, so in the NoSQL world, it's very common to denormalize data and repeat data on essentially cache data inside documents. There is always a trade-off, and the decision here is uh, the decision to cache the data inside a document instead of joining documents is quite often according to how you query your data. So how often you will do this kind of operation. So if you use this data, let's say in every single page, you load your user from the database, you probably want to avoid joins. And then caching will be a good approach. If this query is not something that you do that often, it's okay to just have a ID reference in another document and make a join as well. Another way to tackle this is to have a proper index in place, because if you have if you decide to say no, I don't want to cache data inside my document here, so I always want to go to the other document and get the data from there as well, enjoy those documents. You can create an index that will compilate the data between those two documents. So when you need to make this join, the query planner inside the database will not go to this document, it will go directly to the index. So your performance will be as good as if you have a model than in a relational database. So that's pretty much it. See you guys. Bye bye.